So welcome everyone to the collaboration session of IEEE VR 2022. So my name is Wallace and I'm going to be the chair for this session. We have three very interesting papers presentations and they will present back to back. And at the end, we have time for questions and for a discussion. So as you have questions, please post them on the Discord channel for this session. You can find it under paper sessions collaboration. At the end, we'll go through all the questions. And I would like to start the session by introducing our first speaker, Marina Medeiros, which will be presenting the potential of VR-based tactical resource planning on spatial data.
So, hi, I'm Marina, and I'll be presenting our paper. I would like to say also that Bettina Schlager, my colleague, she is also in the session, and she will also be answering some questions in the Discord channel. So I'm now going to share my screen. Please let me know if you don't hear this sound.
Hello, my name is Marina Medeiros. I am a researcher at VRV.
Just 1 second.
Research Center in Austria and a PhD student at TU Vienna. I am excited to present the design, implementation, and evaluation of a collaborative VR application for tactical resource planning on spatial data. Tactical resource planning is a common task executed during a military staff exercise, a simulation-based training that involves interdisciplinary high-level military personnel. Participants work in groups under the coordination of a commander to plan tactics based on a fictitious crisis, for instance, peacekeeping, humanitarian operations, rescue tasks, or defense. A standard tool used for the decision-making for tactical planning tasks are 2D or 3D maps. Though 2D maps have some evident shortcomings. First, there is limited support for height information. Other terrain information, for instance slope or height, is complex to read. Users often rely on depth cues communicated through shading or surface topologies to derive information. Current paper map alternatives can be grouped in three categories: desktop-based displays, projection-based setups, and head-worn displays. Compared to the other two, head-worn displays provide increased spatial understanding through higher immersion, 3D perception, and realism, and in relation to 2D displays, improve the perception of complex structures. In this work, we focus on the design of a three-dimensional planning environment for tactical resource planning, leveraging the advantages of immersive systems. First, we held consultations with experts of the Institute of Military Earth Science of the Austrian Army. With them, we discussed basic technical requirements, such as the data format and structure of the terrain data. Further, we conducted a field study in which we passively monitored the behavior of officers during a staff exercise. During mission planning, all groups work on a current task collaboratively. Every group was dedicated to the staff of one discipline, for example, intelligence or logistics. The result is drawn on a transparent sheet overlaid on the map. The officers present their tactics to the commander using the transparent sheets created during mission planning. The commander then gives them feedback and suggestions. From the initial field study, we decided to implement an asymmetric collaborative setup, a system that supports different resolutions of terrain data, and we defined two use cases for our application: terrain annotations, inspired by the transparent sheets, and visibility and quantitative analysis of terrain information. Our prototype is based on the game engine Unity. At start, we imported terrain data, previous annotations, and project relevant metadata. The annotation information can be exported by the user anytime. As you can see on the right image, two users can work with the system at the same time. The desktop operator can see a mirrored view of the VR user and interact with an orthographic top map view. We implemented different awareness cues to support users' collaboration. A pointer for the VR user used to query terrain and annotation information, Further, the desktop operator can observe the position of the VR user on the map and see a first-person view from the current gaze of the VR user. As you can see on the bottom right, the VR position and gaze are shown in the map view through an avatar. Overall, the work environment for both users is synchronized. We will now show a video with the features of our application prototype. In the video, the desktop map view is represented on the left side and the gaze of the VR user is on the right side of the screen. This video shows what a desktop operator would normally see using the application. You will see both users working together in a synchronized environment. For the locomotion, we implemented 3 different techniques: standard teleportation for short distance traveling, 3 degrees of freedom steering, and the world in miniature metaphor for long distance traveling. Based on our field study, we implemented features for 2 use cases. The first one is map annotations. Overall, we assigned the annotations to layers, which resembles the transparent sheets used in the staff exercise. We implemented 4 annotation types: points, polylines, polygons, and standardized NATO markers. Both users can place those annotations on the terrain. The second use case used features for quantitative analysis on the terrain. Both users can query distance between 2 points or area of a polygon, use mouse or raycast input. We also provide a line-of-sight visualization feature. The user in VR can drag a wide sphere to choose a location on the map. From this point, the line of sight of that point is shaded in green. To evaluate our prototype, we conducted semi-structured interviews with 3 cartography experts. Prior to the interviews, the experts were able to field test our prototype at different staff exercises in second and third quarters of 2021. The interview suggests that VR provides an enhanced understanding of terrain data for non-domain experts. Some implemented features stood out as especially useful for tactical planning on spatial data, for example, 3D drawing and terrain measurements. Last, using the VR environment, users can place annotations more precisely. In comparison, on paper maps, annotation could occlude other information and have a fixed resolution. Further, the potential is dependent on non-technical circumstances such as user attitude, prior experience, and interoperability. In future work, we want to improve the interoperability of a VR system with other software to allow an uninterrupted working process. Also, due to the COVID-19 pandemic, we were not able to perform a user study. So in future work, we will include a quantitative and qualitative usability study to understand the bottlenecks and merits of our 3D interaction design. We would like to thank you for your attention, and we are eager to discuss more about our findings and answer any question.
Thank you very much.
All right. Thank you, Marina. And now I'm going to introduce the presenter for the second paper. Zhang is going to present virtual workspace position techniques during teleportation for co-located collaboration in virtual reality using HMDs.
Yeah, thank you for the introduction. Okay, so hello everyone, I'm Yiran. I'm happy to be here today to present our virtual workspace positioning techniques during teleportation for co-located collaboration. And this work was accomplished by the University Paris-Saclay and the IMT Atlantic in France. In many collaborated VR applications, the co-located users often have their relative position in the virtual environment, matching the one in the real world. And the resulted spatial consistency enable the possibility of introducing a tangible interface to the user. For example, as we can see here, a shared prop can be integrated in a virtual windshare or virtual car hood assembly task to coordinate the user's co-manipulation. In addition, the spatial consistency allows the co-located users to interact directly with each other, such as performing a handshake between them. However, the required one-to-one mapping constrained the use of the virtual navigation since it can break the spatial consistency. As a result, the users can only explore a virtual environment of limited shape and size. Moreover, the user's individual tasks often have to be removed from a continuous workflow of a complex collaborative scenarios. And this work aimed to help overcome these limits by allowing users to recover the spatial consistency after individual teleportation, so that the users can re-establish their position in the current context of the collaborative task. And we choose teleportation since it is widely used navigation technique. Moreover, it can lower the simulator sickness and discomfort compared to other techniques. In our approach, we deploy a virtual representation of the user's shared physical workspace in the virtual environment, and we use a preview avatars to show how the users will land after the teleportation. And by positioning the virtual workspace, the users can define an area to recover the spatial consistency regarding the requirements of the subsequent collaborative task. And as the collaborative interaction can be symmetric and asymmetric, we propose two different strategies. And the first one, which is the lead and follower technique, allowed one of the users to position the virtual workspace, while the other users can only communicate verbally their requirements. As we can see here, the intersection point between the virtual ray and the virtual ground will determine the position of the virtual workspace. And the leader can also rotate the virtual workspace around their preview avatar by sliding their finger in a circle on the touchpad. And unlike the first technique, the co-manipulation technique allowed both users to control the virtual workspace. And in order to pull the virtual workspace towards the user's desired configuration, we consider that the user-defined target position and the user's preview avatars are connected by a mass bring-down system. Besides, we use a bending rate to continuously inform the users about their mutual actions during the whole manipulation. We compared these two techniques in a control experiment and formulated the following hypothesis. First, we assume that the users will spend more time to discuss the future workspace position in the leader and follower condition. And second, we expect that the co-manipulation will induce the better workspace positioning and resulting in a better performance for the revisiting task. And finally, we expect to find a power imbalance between the participants in the leader and follower condition. The experiment follow a waiting subject design, and we recruit 12 pairs of participants. The experiment setup consists of 2 HTC Vive Pro connected via network, and the 3x4 tracking space of the two users are aligned to a common coordinate system by a calibration procedure. And in this experiment, participants need to first perform individual preparatory work for the team revisiting, where we can see one of the participants has to teleport to the charging station to charge the hammer, while the other teleports near a shelf to obtain the revise. And after they returning to the team revisiting area, participants had to position their virtual workspace. And individual criteria for the future virtual workspace position were provided differently to the participant. And participants had to position their virtual workspace to enclose all the required reverting points. And after arriving at the newly positioned workspace with the recovered spatial consistency, the team revisiting task began. As the end of the relay and the hammer were respectively mapped to the upper area of the controller, participants could feel the heat when they harmed the relay. Participants need to try two conditions as two subsessions. Each subsession includes 3 trials in a randomized order, resulting in different optimal virtual workspace position with 3 rotations. And in the experiment, we measure the task completion time, the workspace positioning time, the revisiting time, the number of the position and the warnings. And we also measure the user's cognitive load, their leadership, contribution, and talkativeness with questionnaires. And the result provide evidence that the co-manipulation was more efficient as the participants spent significantly less time on completing the task. In particular, the time used for positioning the workspace was significantly reduced, which support our first hypothesis. However, we were not able to find any significant difference between these two techniques in terms of revisiting time, which does not support our second hypothesis. And participants agree that it was the leader who directed the workspace positioning. However, no significant difference in levels of verbal activity and contribution was found, which does not support our third hypothesis. To conclude, this paper proposed 2 interactive techniques that allow the co-located users to recover spatial consistency after individual teleportation. We compared these 2 techniques in a collaborative revisiting task, and the results show that the positioning of the virtual workspace can be significantly faster with the co-manipulation than with the leader and the follower. However, the co-manipulation also introduced a conflict in the way to position the virtual workspace. For the future work, one can consider to extend the recovery techniques for more than 2 users. Besides, different spring damper values can be tested in the co-manipulation condition, which can give the user some balanced control over the workspace positioning. And also further investigation are necessary to determine which technique is more appropriate in different scenarios. And finally, we can continue to work on the recovery techniques for other navigation metaphors such as steering techniques. Thank you for your attention.
Thank you, Yiran. Okay, so now for the last paper and third of this session, we have Kevin Yu, which will present duplicated reality for collocated augmented reality collaboration. As before, please post your questions to Discord, and we'll ask the questions for all the speakers at the end of Kevin's presentation.
Did you ever find yourself in a situation with someone and you want to show them a task, but the other person is occupying the space? You have to tell them, please move aside, I can show you how it's done. My name is Kevin Yu, and today I'm presenting our concept of duplicated reality. Duplicated reality intends to relax physical constraints of shared space by duplicating the perceived reality. The concept is quite straightforward. You select a three-dimensional region of interest in the real world, and the duplicated reality replicates the content of a physical world inside a digital copy of it. This way, 2 or more people can work in the same physical region without interfering. In contrast to related work using 2D monitors or virtual reality, for creating such consultation is that you are allowed to stay within the same physical area. This would allow both users to participate in the task and easily switch roles as they find fit. You can point at things and draw annotations, and your partner can see in real time your intention through augmented reality visualization. In our work, we are looking at a surgical use case, particularly the pedicle subtraction osteotomy. The typical patients requiring the PSO surgery are women around 60 years old with severe round back problems. By removing part of the spine, they can regain a healthy posture again. PSO is a complicated surgery, even for experienced surgeons. However, studies showed that having 2 collaborating surgeons on site can improve surgical outcome. AR is a powerful tool which can help to communicate complex 3D matter. In a surgical environment, however, people need to coordinate physical space to avoid interference. Adding an AR system for creating 3D annotations comes with problems. People may need to walk around the table just to draw 3D annotations, and annotations cannot be placed easily underneath the physical surface. Using an AR-enabled device close to a patient would additionally require effort in patient safety and sterilization. Now to the technical part. These are the components and spatial transformations. We use a HoloLens 2 for showing augmented reality content and Azure Connects to acquire the 3D information of a real-world environment. All components are calibrated into a common origin. The point cloud of the Azure Connect are triangulated in real time and used for generating the content of a duplicated reality. Please refer to the paper for more details. This is now a live simulation for acquiring the content of a duplicated reality. We deploy a virtual RGBD camera. Here on the left, you can see the depth image, and on the right, the color image of a virtual camera. Both cubes can be dynamically moved and scaled. And annotations are visible in both cubes. The participant's task is to reenact a PSO surgery, but in a very simplified manner. We have to use a blunt tool to form a block of kinetic sand into a given shape that resembles the steps of a PSO surgery. We compare our concept with a baseline condition, where both users are forced to work at the same physical location. Each user assumes a role. The surgeon works on a sand block, while the co-surgeon guides the surgeon through the steps of her operation. In reality, both roles would constantly change, and there would be no clear distinction between both roles. In our study, the co-surgeon and only the co-surgeon can see the desired PSO shape on the block, since it represents the exclusive knowledge of an expert. He assesses a number of quantitative measures, and record the user's pose. We found that only the awareness of a consulting person, also known as the co-surgeon, show a lowered awareness on the current events surrounding the original region of interest. All other measures in our study were not significant. This is a heat map visualization of one randomly selected pair of participants. Red indicates a high duration of space occupancy. Next, here's a heat map of a co-surgeon. And here you can see a playback of their behavior during the task. You can see that the co-surgeon preferred to stand most of the time at the head of the table to avoid interfering with the surgeon. Here's the heat map of the same pair when using duplicated reality. And again, the heat map of a co-surgeon. And this is the playback. Here you can see that the surgeon would switch between the side of the table, but is much more condensed to specific spots. This is because the surgeon does not have to share the same space with the co-surgeon anymore. The co-surgeon here is now much more agile in their movements. Based on the results and feedback of the participants, we find that users quickly understood the new concept and its interaction. A lowered awareness can be anticipated because the method drops out all information outside the region of interest, including information where the other user is currently located or currently doing. Therefore, we believe our concept is interchangeable with conventional AR visualization by providing the benefits of relaxed physical constraints. We observed that when users are unfamiliar with 3D mid-air drawing, they tend to draw lines with a wrong depth based on their viewpoint. When the same line is viewed from a different angle or the perspective of the other user, the wrong placement becomes very apparent. If a user is unaware of this, it may have resulted in inaccuracies during the task. We conclude that duplicated reality benefits from relaxing physical constraints, real-world constraints, while barely affecting the perception of a task and the task results, except a lowered awareness on the consulting side. For future work, we can imagine it to be used for more tasks beside the surgical domain that have small available working space or hard-to-reach locations. With this, thank you for your attention. I think you're muted.
All right. Thank you so much for the presentation. It was awesome. So let's go to the questions here. Okay, I see here a question to Marina. So it says, I really liked how you motivated the use of 3D for the tasks necessary in the military domain, and how you integrated VR and desktop views for collaboration. So there are two questions. The first one is, what kind of users are you planning to use in the next studies that you mentioned at the end of the presentation? And then would they be students, again, military users, or experts from different domains as well?
Yeah, for right now, we are planning to do with military students, actually, because one of the difficulties that the Army actually have, like the Army institute that we work with, they are responsible for creating the maps. They are used in the mission planning. They are responsible for all the materials. So it's a map, and then they have the VR option. The problem is that the students, they learn how to do it with a paper map. So they are used to use a paper map. So now we are trying to do a user study with the students from the military academia from the military school, sort of saying, to then try to create this co-sharing side of the army, to start using VR, because the potential it has been proved, at least that the potential for them is clear, but for the military institute that actually works with ours. So there are other sections in the army that needs to be more engaged in the VR process. But I personally also have some ideas of using this with architecture students, but that's something that is really just an idea. But I think that this kind of application where you can see a 3D model, reconstruct 3D model, would be very useful also for urban planning and something related to planning in general, when you have you actually use a 3D model for that. Did I answer all the questions?
I hope so. This was asked by George Wagner. So if not, he can ask again.
He can ask again.
But I think it was a good answer. Okay, Yiran, I have a question for you.
Yeah.
So in your study, you have like 2 participants collocated, and you're actually trying to make them share the same reference to like physical objects in space. And you have a part where they actually need to touch controllers with each other. So were participants afraid at all that they would like walk onto each other or hit other participants with the controller? Were they afraid to walk without seeing?
Actually, the idea of the spatial consistency recovery is help to users to establish like more the confidence for the system, because as we all know, like in a co-located collaboration scenarios, if both users are provided with individual navigation capabilities, and there will sometimes be some spatial desynchronization, which means their avatar and their real users, there's an offset. And in these times, like when the user are approaching together in the real world, but actually their avatar in the virtual environment can be really far away. So normally this situation will trigger some warnings. And in our case, actually we avoid this problem. We try to help them to recover the spatial consistency, so their avatar and the real user can be at the same position, so they can like have some physical direct interaction with each other, which can help them like to perform the collaborative task. Yeah, so this is actually the idea, like to increase their trust of the system.
So and do you think that was effective in the end then, that they were like comfortable interacting with the other?
Yeah. And we think like if the passive haptic feedback can provide them like with more immersive VR experience, and that's also the motivation of our study.
Awesome. Thank you. Kevin, so you commented on the difference between like a co-located task and a remote assistant scenario. Do you think you can talk a little bit about it? Do you think we could just move like the expert in your system to another room and then stream the audio and have them working together with the same performance? Or do you think something would be lost and it would be much worse to do it remotely than in a co-located setting?
I think there are multiple aspects. So of course you can move it to another room, but however, you cannot interact with a real task anymore if you are located in another room. Then you have to, you can basically cannot take in the role of a surgeon anymore, the person acting on the region of interest. You are forced to stick with a role of a remote expert. If you are both in the same space, you can still use this metaphor of remote consulting, but you can still switch roles as you find fit. So the co-surgeon can immediately change to the surgeon if, for instance, he can do it better directly. Yes.
Awesome. Okay, let's see here. Okay, so Marina, I think there's a more clarification question. Did you have like the authors actually try the system that you built, and if so, how long did they actually use it?
Who tried? The guys from the Austrian Geodesen Institute, that I think it's geodesy specialists. So what happens that they are our clients, so they ask for the application. We discussed with them. They are the experts, the first experts that we make the consultations, and then we deliver it. And then we also delivered with a guide, a user guide. They used it, and then what happens that they are, since I said like they are the guys who prepare all the maps and all the material, also the 3D models, if they request any 3D models, if it's going to be visualized in VR or not, but if they want a 3D model of some terrain, they are the ones who prepare it. So they always are showing VR as an option in those staff exercise that are those planning exercise that they make with different experts in the army. So they have been, it has been used. It just haven't had a user study structure, but from the interviews we did was from people who saw a lot of people using it, and there's their impression from what they got from the users.
But how
it has been used for
how much time did they have to try out the system? For how long they tried it?
I mean, because actually there was a first version of this project delivered in 2019. Yes, 2019, in March of 2019. It was not as complete as this one. And then there is the second one was from March 2020 to 2021. Yes, March 2021. There's a pandemic. I cannot really remember. Yeah, from March 2021 up to November, that's when we did the interviews. So they had around like 6 months or more to they tried themselves and to present to other staff.
Okay, that's really nice. And so that's another question. Why did you decide going with an like asymmetric design from the beginning? I mean, can you speculate of how the collaboration would happen if you have like the two users inside VR rather than one in the desktop and the other one in VR? Which benefits or disadvantages do you think would appear?
Yeah, I think first of all, they only have one VR headset that they carry with them. And so there is always be someone that has to prepare this 3D model and load the 3D model. So it's not something that they have a lot of headsets that is like distributed and everybody can use it. And I think also secondly is the whole structure of the army itself. There is always a commander. And for example, I think the first version we sent, we thought that they would be working, that there was also not going to be a structure in this work together. But no, actually sometimes the commander is in VR and he just wants to check what other people did. So they are asking very quickly for this and this and that. So there is also the desktop user was there also to be able to turn on and turn off layers very quickly and give this impression to the commander of the whole plan. So that I think was one of the issues. Like they also have like for now, they think a lot about using AR in the future to have like a table, and then you would have a lot of people walking around the table with a 3D model on it, like it is now in VR. And then I think we could have like more users working together, like users in the same level or visualizing only the 3D model and not the map.
Mm-hmm. Awesome, thank you. Yeah, so you have the participants split between like doing the co-manipulation and the leader follower, right? So my intuitive idea is that if you're the leader and you decide when to rearrange the boundaries, then it will feel very good for me. But if I'm not the leader and someone tried to arrange it, that's not so good. Does that matches with what we observed? Do you think that the ones that were leader doing the leader follower condition liked it more than ones that were not the leader?
Yeah, we observed this situation actually, but in our task, actually, we provide the individual criteria for the workspace positioning for different users. So each user has known a part of the required reverting position, which means we encourage them to exchange the information. So they need to communicate where should I put the workspace. So, but still, I think that most of the leader, they prefer the leader and follower situation. That's for true. And I think this technique is also, I mean, the leader and the follower is also interesting in some different scenarios. For example, we can imagine like in some situation where one user is aware of all the requirements of the subsequent collaborative task. For example, in some museum visiting tour, so the guide can in charge of positioning the workspace. So this is a kind of a scenario which this technique can be applied to, and also in some asynchronous collaboration interaction. For example, there's one of the users who position the workspace, and they can go inside and leave a tangible prop inside it. And after there comes another users coming to the scene, and he or she can continue to use the prop that the previous user leave inside the workspace. So this, like the leader and the follower, can also be used in different scenarios. And that's why we think we need more user study to evaluate these two techniques. Yeah.
For sure. So in the co-manipulation condition, the design you have is like similar to two people sharing a same physical object, right? So it's like I hold one part of it and the other user holds in another part. But in this case, it's not a physical object, right? It's the tracking space. If it were a physical object, right? And we were trying to, I don't know, move a desk through, through a door, I can feel like where you're pushing, right? And I can negotiate because I can haptically feel, right, where it's going. Do you think the participants were able to figure that out as well, just by looking at where the space was going?
Well, I think if we try to add some tangible prop inside the scenarios, the main limitation is like the possible solution for the workspace positioning can be limited, because like besides the two users, there's also a tangible prop which the two users need to access to. So which will actually bring some additional constraint when you're positioning the workspace. But once the spatial consistency is recovered inside the space, the two users can, as you said, like to access to the tangible prop and to co-manipulate with it. So, yeah.
Awesome. Thank you. Okay, so question for Kevin.
Yes.
Okay, so in this study, you constrain the conditions so the users would either be in the DR mode or in the counter condition. In a like a natural setting, if they were actually using this, right? Do you think you would see them swapping, you know, the two roles between the two conditions like multiple times during the actual surgery? Or
I think in the real surgery, they would really quickly switch roles multiple times, even because if you have two collaborating surgeons, then maybe one is a neurosurgeon, one is an orthopedist, but they have complementing knowledge, but both are experts in their field. So this is why, depending on the phase and the workflow of a surgeon, they want to quickly change expertise and therefore complementing with each other. So there will be maybe not an entire phase that's only dedicated for the neurosurgeon and only another phase dedicated for the orthopedist. This may not be the case. Yes.
So during the surface like reconstruction, right? So you have a camera on the top, like
Yes.
Filming and reconstructing the surface. I mean, in real life, I need to be aware where the other person is, right? Because if I want to show them something, I don't want to put myself between what I'm showing and the person, right? But in your case, you have something else, which is the camera, which is not in the same position that the other person is in the space, right? And if I want you to be able to see something, I have to maybe remove my hands. Or do you see that kind of negotiation, like in which they were aware where the camera was and like maybe taking their hands off? So there was no occlusion. How does that work in this study?
Well, it definitely is a problem, like occlusion, what you mean. So in this case, it really depends on where you place your cameras that are looking at the space. So usually from top down, it's not a huge problem. Also, you have cameras sometimes in these operating lights that you see. So you could also put a camera inside there that has usually unoccluded vision to the region of interest. What you could also do or consider as a future work is to utilize the depth image and the color image of an HMD that the surgeon actually is currently working. So as like a mobile RGBD camera. Mm-hmm. And that would allow at least to always have a view onto the region of interest. The hands are another problem. You cannot fully avoid that. Yes, that's true.
Mm-hmm. Yeah, I mean, that's something that happens in real life. So it's not
exactly.
It's not a big problem. People cannot see through my hands.
Exactly.
One thing that I noticed about your system is the ability of the expert to make it larger, right? Because that's not something that you can do in real life.
Yes.
Do you think they use that feature a lot? Did they thought it was a good thing?
I think it's a good thing. I actually recorded it. It's also in the paper. So the participants unconsciously increased the size to about 1.5 times. And this is just a value for them to feel comfortable to place these kind of annotations. So I think it has a real value there.
Very interesting. All right, let's check here. Okay, I have a final question for Marina here. So in the desktop view, the person who was in the desktop, they actually had two views there, right? One which was the top view, and the other one which was the view of the person in the HMD. Right? Did you notice how they use both of these windows? Did they focus just on one, or did they find it better to look at both? Did you find it was actually useful to have both views?
I think it's definitely useful because usually the VR user is the one that is not experienced in VR, so they might get lost, or they might not know how to use the menus or something like this. And so it's always very important that the desktop operator, as we call it, like knows what the VR user is doing. Also, sometimes they can fix something that they did, make some mistakes or something like this. The VR user can also fix stuff like erase and do, but like, yes, the desktop would be the most experienced one, I would say so. But for this case, like for this case, but I cannot really tell how they use it, because if they are always, because they can actually slide, to have more of the screen showing the map, or they can show more of what the VR user is doing. I cannot tell like how they use usually, like how they that's a question that we should make for them. Mm-hmm. They can also split this in two screens. That's also something that they can do. But one thing that the desktop operator can only do is that they can only work in the map. They cannot go into like the 3D view of the terrain and place a marker, for example, or make some measurements. They can only work in the map view. So that's how they include stuff. only the VR user is the one that can add stuff like in 3D.
Awesome, thank you so much. So with that, I want to conclude this session. I will thank again Kevin Yu and Yiran Zhang and Marina Medeiros for the presentations. Thanks for everyone who attended and asked questions to the speakers. And feel free to continue having discussions with the speakers and other participants through Discord and through the social Zoom sessions. And have you all a great conference.
Thank you very much.
Thank you very much.
Thank you.